Hello, good evening, everyone. My name is Ranjan Bora, and I am one of the teaching assistant in this course, Biomechanics of Joints and Orthopedic Implants. And from the starting of this course, I have been taking the weekly. I have been taking the tutorial lectures in every week, every Friday from 6 to 8 p.m. I have already taken tutorials for the past 2 weeks. So today is the week 3. And if you have missed my previous tutorials, those tutorials are uploaded to the YouTube channel, and the links to those videos have been, you can access those videos in the NPTEL web page. You will get the links. So using those links, you can access those videos. And last week, I have discussed about degrees of freedom and kinematic chain and open and closed chain mechanisms and problems and solve some numerical problems. So today, first I will solve the assignment from week 2, and after that I will solve some numerical problems from the previous week 2. So so I will start now. First, I will solve the assignment from week 2. I hope you have already submitted, so you can easily tell me the answers. So first question is, which movement involves results in decrease in the angle between forearm and upper arm in the elbow joint? So what is the answer? Yeah, flexion is correct. So you can see this is a elbow joint. So question says about decrease in angle between forearm and upper arm. So this is the angle. If we represent the angle with theta, so by doing flexion, this theta is getting decreasing, and in extension, theta is getting increasing. So here, flexion is the correct answer. And next question, which of the following muscle is not active during elbow flexion? Yes, triceps brachii is correct. So you can see the muscles which are involved during the elbow flexion are shown here. Like the main muscles are brachialis, biceps brachii, and then brachioradialis. And in this figure, you can see where are these muscles located in our arms. And triceps muscles is not involved during the flexion activity. So option D is correct. And the next question, carrying angle is the angle between the long axis of, what is the answer? Yeah, C is correct. So you can see in this figure, the carrying angle means the angle between the long axis of the upper arm and then this forearm. So option C is correct. This is the carrying angle. And what is the degree of freedom corresponding to humor ulnar joint? Yes. So you can see this is the humerus, and this is there are two bones connecting with the humerus. One is radius and one is ulna. This humero-ulnar joint, it allows only flexion extension. But this radio-ulnar joint, it allows both flexion extension and then pronation and supination. So with respect to this humero-ulnar joint, there is only 1 degree of freedom. So that's why option A is correct. Next question, what is the degrees of freedom of the shoulder joint with respect to thorax? Yeah, 6. So you can see shoulder joint, between the shoulder and the thorax, there are 4 joints mainly, uh, but the main means connecting with the thorax, there is one glenohumeral joint. Here it is the glenohumeral joint, and there is one sca scapulothoracic articulation. So here, so only these 2 joints with respect to thorax, we get 3 degrees of freedom at glenohumeral joint and 3 degrees of freedom at this scapulothoracic articulation. So total 3 plus 3, we get 6 degrees of freedom. What is the angle between the long axis of the femoral head neck and the transverse axis of the femoral condyle? Yes, angle of antiversion is correct. So this, if we see in the frontal plane, it looks like this. So this is this view is top view of this. This is the top view, and this is the front view. So this angle, long axis of the femoral head neck and the transverse axis of the femoral condyle. So if we look this femur from top, then we'll get this type of view, and this angle is called the antiversion angle. The simultaneous motion of shoulder girdle and humerus is known as, yes, it is both scapulohumeral rhythm and glenohumeral rhythm. And next question, the connection thorax clavicle scapula is a what kind of mechanism? Yeah, closed chain. So you can see the scapula is connected to both the clavicle and thorax. So it is a closed chain mechanism. And next question is, kinematic chain is an assembly of rigid bodies connected by joints to provide, yeah, constrained motion. So kinematic chain is an assembly of rigid bodies connected by joints to provide constrained motion. I have discussed the more about kinematic chain in my last video. So you can watch that video if you have missed my previous video. Next question, push-up is an example of, yeah, closed chain. Like you can see, this is the schematic of a person doing push-up. So if we represent these bones using some links, so how we can represent this? We can represent this whole hand as one link, then then the right hand is another link, and between this and the shoulder as a one link. So these terminal links are fixed here, means constrained here. When the terminal links are not constrained, then that the chain is known as open chain, and when the terminal links are constrained, that chain is known as closed chain. So push-up, in this push-up, all the terminal links are constrained. That's why it is an example of closed chain exercise. Next question is, which of the following factors influence the joint degree of freedom? Yes, both the shape of articular surface and the number of ligaments. And what is the degree of freedom of the glenohumeral joint? Yeah, so it is a type of ball and socket joint. So ball and socket joint has 3 degrees of freedom. So this glenohumeral joint has 3 degrees of freedom. And which is the major load bearing joint at the shoulder? Yeah. So you can see at the shoulder we have 4 types of joint, but the main joint which is connected with the arm humerus is this glenohumeral joint. And when we carry some load with using our hand, so the load is first getting transferred through this glenohumeral joint. That's why it is called the major load bearing joint. And the next question is, the patella allows a wider distribution of the compressive force on. Yeah. So you can see the because of the patella is this distribution gets wider. Means we have this patellar tendon. If there is no patella, then it will be limited up to this region only. Because of the patella, we are getting extra uh, more distribution of the compressive force. So it is because of the patella. And next is the patellofemoral joint is subjected to, that is the resultant summative force of the vectors of the patellar tendon and the quadriceps tendon force. What is the answer? Yes, compressive force. So you can see here there is patella, and this patellar tendon force is acting in this direction and quadriceps force is acting in this direction. So resultant force is acting in this direction. So it is a type of compressive force. It is trying to compress this femur. So that's why option A is correct. Next question is, hip deformity refers to decreased femur neck shaft angle less than 120 degrees. What is the answer? Yeah, Veras. So these are the type of hip deformities you can see. We have this coxa vera, in which the angle is less than 120, and in normal case we have angle in the range of 120 to 135 degree, and in coxa belga the angle is equal to 125 or greater than, it should be greater than 125. So this is option B. Next question is, the peak knee joint reaction forces during normal walking is in the range of dash the body weight. Yes, B is correct. So in these slides, you can see this table. This table is taking from these references. So during the normal walking, means this level walking, this is in between these 200 to 300%. So option B is matching. Okay, next there is one numerical problem. So here what is given, W is given 60 kg and B is given 0.25 meter and C is 0.1 meter. Now we need to calculate the abductor muscle force Q. Hip joint center is denoted by H as shown in figure. So like what in my previous class I have discussed this kind of problem. Yeah, I am going to first solve, then I'll verify. So what we need to do first, we need to draw the free body diagram. This 5/6 W is acting at a distance of B, and Q is acting at a distance C. And hip joint reaction force will act along this direction. Now we'll take moment equilibrium about point H. Summation MH equal to 0. And we'll take clockwise as positive. So because of this 5/6 W, we are getting clockwise moment with respect to point H. So 5/6 dot W is given 60 kg, but unit is given kg, so we need to convert it into Newton. 60 into 9.8 into B, and because of Q, we are getting moment in anti-clockwise direction. In this, it will be negative minus Q dot C equal to 0. We are not getting any moment because of this J, because J is acting at that point only, about which we are taking the moment H. From this, we'll get Q equal to 560 and 0.8 into 0.25 divided by 6. C is given 0.1. It is coming 1225. Because I have taken Z as 9.8. If you take Z as 10, you will get this B, option B. Okay, moving forward. Next question. Which of the following is affected by femur neck shaft angle? Yes, both the joint reaction force and the lever arm of muscle force. How it is getting affected, like you can see, this angle is called femur neck shaft angle. So in this case, the joint is located here and abductor muscle will be somewhere located above this. And in this case, joint position will be here, abductor muscle force will be here. So you can see this muscle, muscle moment arm of the muscle is getting reduced. So because of this, the joint reaction force means there will be effect on joint reaction force also. So option C is correct. And the last question is, which of the following is the movement of the spine? Yes, Option D. So what are the movements of the spine? These are flexion, extension, then lateral bending, then rotation, left and right. So these are the three types of movement in the spine. So is it okay? Do you have any doubt you want to ask? Okay, good. So now I will solve some numerical problem. Okay, there is one problem related to this therapeutic intervention for a painful or mechanically unstable hip. This is the question. The hip joint is as shown in the figure, suffers from chronic pain. This side, this joint is suffers from chronic pain. If the person is to take the support of a can for walking, on which side he should hold the can? The person holds the can at a distance of 10 centimeter from the hip joint. So if he takes the help of a can for walking, so which side he should hold his can to experience the minimum amount of force in this hip joint? So that we'll find out through this problem. So these are the given data. D is the momentum of this abductor force, hip abductor force, and D1 is momentum for body weight, and total upper body weight is given 760.6 Newton, and abductor angle is 13 degree. Abductor angle means this angle. Angle between the abductor muscle force and the vertical line of action. This is 13 degree. Now we need to calculate the hip joint reaction force for a can force of 76 Newton. So when the person takes the can, and there will some reaction force also at the can. So this can force is given. Sorry, this is 76 Newton. Okay, there will be two cases. Like either the person will take the scan on this side, on the on the same side of the hip joint, or on the opposite side of the hip joint. So we'll solve both the cases. So first case is this is case 1, and this will be case 2. So case 1 is can is same side of affected hip joint. So in this case, how will be the free body diagram? So I'm drawing. Let be this point be O. The hip joint center point is O, and this point is O, and body force is acting at a distance of D1. Body weight is W. This is D1. Then abductor muscle force is acting at a distance of D. and he is taking the can on the same side. So this is can, and can force is acting. See, this is acting at a distance. This is given. The person holds the can at a distance of 10 centimeter from the hip joint. So I am representing hip joint as O. So this distance is 10 centimeter. Okay, and there will be hip joint reaction force along this point, along this direction at the point O. So now I will do the moment equilibrium about point O. And we will take clockwise as positive. So this W is producing moment in the clockwise direction. So this will be W dot D1. M is producing in the anti-clockwise direction minus M dot D. And can force is also producing in the clockwise direction about this point O. Plus C dot, I am writing directly the distance 10 equal to 0. Now I will put the values. W is given W is 76.6, sorry, 760.6 dot D1. D1 is 8.64 minus. This muscle force is not given. So first we need to find out this abductor muscle force. M dot D. D is given 4.39. 4.39 plus C is given, C is 76. The force applied by the can. 76.10. So using this, we'll get M. How much will be M? M will be 760.6 plus 760 divided by 4.39. It will be this is 1670.06 Newton. So the abductor muscle force is acting this amount of force. Now we have got the abductor muscle force. So now we can find the joint reaction force J. So how we can find the joint reaction force? We know this angle. This angle is given 13 degree. Okay, now we can apply the vector method. Like we can take these three forces, M, J, and W, and we can represent it using a vector triangle. So M will be this, and W, and this will be J. And this angle is 13. Let us take this angle as theta. So in this case, what will be J? The formula for J it is square root of m square plus w square minus 2mw cos theta. Sorry, plus. Because we are taking theta is this angle. So if we do this, how much will be J? So this is coming 5842.3. Square root of this will be 2417.2 Newton. So the joint reaction force is this much, 2417.2 Newton. So is this clear? Do you have any doubt? Okay. So this was the case one, like the person is taking the can on the same side of the affected hip joint. And we have seen there might be case two also in means in the case two, the person will take the can on the opposite side of the affected hip joint. So now we'll solve the joint reaction force for case two. In case two, the can is on the opposite side. Of affected hip joint. So in that case, again, we'll draw the free body diagram. This is W M. This is T. Now the person will take the can on the opposite side, so it will be. So if we look into the figure, here you can see from the central axis to the left hip joint, this distance is D1. So from this hip joint to the opposite side hip joint, this distance will be twice D1. And again, he takes the cane at a distance of 10 centimeter. So this will be twice D1 and this will be 10 centimeter. So 10 centimeter from this left side hip joint. So it will be 2D1 plus 10. Here it is D1 and from here it is 10. And can force is I think 76. So it is 2D1 plus 10. Okay. Yeah. See, in the question, it is given that the person holds the can at a distance of 10 centimeter from the hip joint. So from the hip joint means if he takes the can on the right side, he holds the can 10 centimeter from his right side hip joint. If he holds the can on his left side, he holds the can at a distance of 10 centimeter from the left side hip joint. So that's why you can see, and we are only concerned about this affected hip joint, which is the right side hip joint, which is shown in this figure. That's why we are drawing the free body diagram with respect to this right side hip joint. And we have already done one case one in which he holds his can on the right side. And when he holds the can on the left side, this distance we are calculating. So this is given D1, means from this central axis to the right hip joint, this distance is D1. And so because it is a symmetric, hip joints are symmetric with respect to the central axis. So the distance between the central axis and the left hip joint center will also be D1. And from the left hip joint center towards his left, he means he holds the can at a distance of 10 centimeter. That's why I have this distance will be 2D1 plus 10 centimeter. So have you understood? Okay. Okay, now we'll take the moment equilibrium about point O. Summation. And here, again, we'll take clockwise moment positive. So W is producing moment in the clockwise. So W dot D1 and M, this abductor muscle force M is producing in the anti-clockwise. It will be minus M dot D, and can force 76 Newton. Now you can see it is producing in the anti-clockwise direction about the point O. So it will also be minus 76 dot 2D1 plus 10 equal to 0. So using this, we'll get M because M is only unknown here. W is given 760.6 dot D1 is 8.64 minus M. D is given 4.39 minus 76 dot 2 into 8.64 plus 10. So from here, we will calculate M. It will be 760.6 x4 minus 76 0.64 plus 10 divided by 4.39. Oh. So it is coming 1024.67 Newton. The abductor muscle force is coming this much. Now you can compare. In the previous case, it was coming, say, 1670. Now it is coming 1024. So you can see the if the person holds the can on the opposite side, then there is a reduction in the abductor muscle force. So now we'll calculate the joint reaction force. Again, we'll directly use this formula. J equal to We are using the formula from this slide, m square. It will be m is 1024.7 square plus w is O was 13. So we solve this. So it is coming 1774.05 Newton. So you can see if the person takes the cane on the opposite side, there is a reduction in the joint reaction force. Previously it was 2417. Now it is 1774. So there is a reduction of 700 Newton. So what the doctor will prescribe? The doctor will prescribe to hold the can on the opposite side. Okay, if you have any doubt, you can ask. Is it clear? Okay, thank you. So we'll move forward. There is one more problem. So this kind of problem is there in the slide. If you have gone through the lectures, then you can see like the sir is solving some problems, similar problems in his slide also. So for your practice, I have taken this problem. So in the question, it is given that flexed position of the arm, and the free body diagram is also given in figure B. Here Fm1, Fm2, and Fm3 are the magnitudes of the forces exerted on the forearm by the biceps, brachialis, and brachioradialis muscles with attachment at points A1, A2, and A3. And theta 1, theta 2, theta 3 be the angles that the biceps, brachialis, and brachioradialis muscles make the long axis of the lower arm, with the long axis of the lower arm. And we need to estimate the muscle forces and humeroradial and ulnar joint reaction forces for this position of arm. So these are some given data like weight of the arm is 83 Newton, and the person is holding a weight of 58 Newton on his hand. And these moment terms are given B, C, and insertion points of the muscles from the axis of rotation of the elbow joint are given, and the distances from the joint axis to the points of action and onto the forces on the humerus are given. So now first you tell me how many unknowns we need to find out. How many unknowns are there in this problem? So what are the parameters we need to find? We need to find the muscle forces and the joint reaction forces. So how many unknowns we need to find? Have you understood the problem? Okay, Pragya, what is your doubt about? Are there two muscle forces difference or from this problem or from the previous problem? Yeah, this problem, there are three muscle forces, the biceps, brachialis, and brachioradialis. So M1, M2, and M3 are the three muscles. So we need to find three muscle forces and two joint reaction forces. So we have total five number of unknowns, five unknowns. So to to get the five unknowns, we need to have five equations, right? Then only we can solve the problem. But we have how many equations? We have the force equilibrium equations and the moment equilibrium equations. We have summation fx is 0, summation fy 0, and summation m0. So we have three equations in our hand. So, but we have five unknowns. So this is a problem of statically indeterminate problem. Statically. So how we'll solve this problem then? So we'll need some additional information. So some additional informations are also given. You can see like there is one assumption that all the three muscle forces are stressed to the same intensity sigma m, and the force produced by each muscle will be proportional to its cross-sectional area. So the muscle cross-sectional areas are given for the three muscles. So means what is this assumption is saying about? Fm will be equal to sigma m dot am. Here Fm is the muscle force and am is the area of cross-section of the muscle. And sigma m is the stress intensity. And this is the intensity sigma m. So for biceps muscles, it will be Fm. Biceps I'm representing would be, it will be sigma m dot 518 into 10 power minus 6. And for brachialis, PR, it will be sigma m dot 493 cross 10 power minus 6. And for brachioradialis, capital PR, sigma m dot 120. So now you can see we have converted the muscle forces into only one unknown, which is sigma m. So all the muscle forces. Now, if we know the sigma m, then we can estimate all the muscle forces. So now we can see there were 5 unknowns initially. Now we are representing the muscle forces in terms of this stress intensity sigma m. So muscle forces are replaced with one variable, one unknown, and remaining the two joint reaction force, we have two unknowns. So now we have reduced this problem into 3 unknowns. Now we can solve this problem using this additional information. Okay, first we'll first we need to estimate the muscle forces. So there are 3 steps to solve this problem. The step 1 is like we don't know the muscle moment term. So first we need to find the muscle moment term. So find the muscle moment terms. So for each muscle, I will find the muscle moment terms. These parameters are given A1, A2, A3, and this distance from the joint axis O to the points of action of forces in the humerus bone are given. So we'll use this information. So first I will calculate for brachialis muscle. Brachialis is A2. So for A2 is given 5 centimeter. Brachialis, okay, I will draw this. Along this M2 will act, and this is given A2, and this is given 0.08 meter. So we'll calculate in terms of centimeter. It will be 8 centimeter. So this is the brachialis is in the ulna bone. So this is the ulna, and this is the humerus. Okay, we are calculating this distance. This will be the moment term, right? If we represent it O, A, B, C, this OC is moment term. So our aim is to estimate this OC. This OC. How we will get that? We'll apply some trigonometric relations. A2 is given 5 centimeter. And so we'll calculate this angle theta. Let this be theta 2. So how much will be tan theta 2? It will be 8 by 5. Okay, so how much is theta 2 then? Theta 2 is 58 degree. So we have got theta 2. Now we can find OC. OC will be how much? This angle is 90 degree. And if we use the trigonometric relation, What will be the cos theta in the triangle in triangle OAC? Cos theta will be, sorry, it will be sin theta. Sin theta will be OC divided by OA, right? So from this we can get OC. OC will be OA into sin theta equal to OA is 5 dot this is theta 2 sin theta 2 sin 58, it will be 4.24 centimeter. So we have got momentum for one muscle. So similarly, I will find out the momentum for other two muscles. Next, other two muscles are brachioradialis. This is represented by A3. A3 is given 24. So for your radialis muscle, this was A2. This is given 20. This is A3 equal to 24 centimeter is given. And this vertical distance is given 6.5 centimeter, and we'll to find this momentum. First we need to find out this angle theta 3. We'll use the same formula. Then theta 3 will be 6.5 divided by 24 from here. Theta 3 will be 15 degree. So if we represent it with OD, how much will be OD? It will be OA3 dot sin theta 3. OA3 is 24. It is coming 6.27 centimeter. Okay, momentum for brachioradial is also found. Next, one more muscle is remaining, which is the biceps. For biceps muscle, A1 is given 3.8, and this is 2 centimeter out from the humerus shaft and 32 centimeter from O. So that means the figure will be something like this. This is 2 centimeter, and this is given A1 is 3.8 and 32. 3.8 and this is 32. This angle is theta 1. So now we'll take this triangle. We need to find out this moment term O E. We need to find out OE. So what is the in this case the tan theta 1 will be 32 divided by we have to minus this 2 centimeter from here, and we have to take this distance. It will be 1.8. 17.8, and we take so theta 1 is coming 87 degree. Now we'll use theta 1 in this triangle OEF. In triangle OEF, again we'll take sine theta 1 OE divided by 3.8. So from here, OE is 3.8 into sine of 87. It is coming 3.79. So we have calculated the moment terms for all the muscles. Biceps, brachialis and brachioradialis. Why we are calculating the moment term? Because to apply the moment equilibrium equation, we need to know the moment terms for each muscle to find out the moment produced by that muscle. So now we can calculate the moment means muscle forces. So from this free body diagram, we'll take the moment equilibrium about point O. So I will draw the free body diagram here. So FM1 is acting here, then FM1, FM2, and FM3, W and W naught, U and W naught, and this is B. This is O. So now we'll take meson of M about O equal to 0. So if we do this, again we'll assume clockwise is positive. So W naught and W, they are producing moment in the clockwise direction. W dot B plus W naught dot C, and all these muscles are producing in the anti-clockwise direction about the point 2 minus FM1 dot. We need to consider these moment terms for FM2, and for FM1 will be this much, and for FM3 will be this. Sorry, it will be So we have calculated this moment term. So FM1, M1 was the biceps muscle. For biceps muscle, the moment term was 3.79. This is the OE, 3.79. Then FM2, was brachialis. For brachialis muscle, the moment term was 4.24. 4.24 minus, and FM3 was the brachioradialis, for which the momentum was 6.27. 6.27. Okay, now we'll substitute the values here. We know W naught B, C, and we have estimated this FM in terms of the sigma M. So we can use this, substitute the values. W is given 83 and B is 16.5. 83, 16.5 plus W naught is 58 and 37. Then FM1 was biceps muscle. It is 518 into 10 power minus 6 sigma M. 518 10 power minus 6. So I'm writing it in a bracket, and means I will take the sigma M out, and it is multiplied by the moment term 3.79. Then FM2 was brachialis, 493 into 10 power minus 6. 493, and the moment term was 4.24. And for brachioradialis, it is 120 10 power minus 6. And the moment term is 6.27. All this is multiplied by sigma M equal to 0. So now we can find out the sigma M. We'll take this minus in and the bracket terms to the right side. So sigma M will be I will directly do the calculation. 33, 10.5. Sigma M is coming 7.31 into 10 to the power 5. And the sorry, this part got erased. So okay, I have already got the values, so no worries. So sigma M is coming 7.31 10 power 5. So using the sigma M, we can find the muscle forces here. So if we substitute the sigma m here, then FMB will be 7.518 into 7.31, and this is 10 power 5, and here it is 10 power minus 6, so it will be 10 power minus 1. So it will be 1. So it is 378.6 Newton, and this is the biceps muscle force, and the brachialis muscle force will be brachialis muscle force is 360.3 Newton, and brachioradialis muscle force is 87.7 Newton. So one part of the problem is done. Like the question it was asked first to us to estimate the muscle forces. So we have estimated the muscle forces. Now we will find the joint reaction forces, the humeroradial and humeral-ulnar joint reaction force. So do you have any doubt in calculation of the muscle forces? Okay. So now I will estimate the first estimate the humeroradial joint reaction force. Okay. You can see while we'll estimate the humeroradial force, in that case, we'll only consider that muscle which insertion point is on the radius. Means we'll consider only these two muscles, biceps and brachioradialis, because the brachialis muscle is not on the radius bone, it is only ulna bone. So for humeroradial joint reaction force, we need to consider these two muscles, biceps and brachioradialis. Humeroradial. So first we need to draw the free body diagram. What are the two muscles? Biceps and brachioradialis, and those are biceps is M1 and brachioradialis is M3. A1, A3, and this weight will be W by 2, because here W is weight given for the forearm, whole forearm. So if we take two bones separate, means radius and ulna bone, this W will be distributed in the two bones. So it will be divided by 2. And for the weight W naught, again, this weight W naught is means when we hold the weight W naught in our hand, between the two bones, radius and ulna. So when we consider the radius bone, it will not be W naught. It will be something less than W naught. So we don't know the value. So we'll assume some constant, means assume some variable. And first thing will be to find out that weight, which will be acting on the radius bone. So here we'll assume, let it be W1 or WR. WR is weight acting on the radius bone. and weight of the forearm is given. We will take at W by 2, and there are two muscles, FM1 and FM3, and we will take the humeroradial joint reaction forces, FJ1, and we'll assume this angle theta with the vertical y-axis, and we know these moment terms. We have find out these moment terms, and this distance is B, and this is C. So we'll write M about O is 0. Again, clockwise is positive, so WR is producing in the clockwise, WR dot C plus W by 2 dot P minus FM1 dot, what was the moment term for biceps muscle? It is 3.79 minus FM3 dot brachioradialis muscle 6.27 is 0. So if we solve this, then we'll get WR. WR will be, FM1 was how much? This biceps muscle 378.6 multiplied by 3.79 plus FM3 is 87.7 multiplied by 6.27. So there will be one more term, which will be W by 2. W is given 83, and B is given 16.5. It will be 83 by 2 dot 16.5, and it will be divided by C. C is given 37. Okay. So WR is coming 35.1 Newton. So 35.1 Newton is means this much amount of force will act on the radius bone. So, and the remaining the total weight that is holding by hand is given 58, and the remaining amount will act on the ulna bone. So we have got WR now. Now we need to find this reaction force FJ1. So how we will find it? So now we need to use these force equilibrium equations. Summation Fx is 0 and summation Fy is 0. Okay, if we use this summation Fx is 0, then, so first I will write the angles here. FM1 was biceps angle. For biceps angle, theta 1 was coming 87. So this angle is 87, and brachioradialis theta is 15, and this is 15. Okay, so now if we do this summation fx is 0, this horizontal x component will be fj1 cos theta. This will be fj1 sin theta. fj1 sin theta, and it will be minus fm1 cos 87 minus fm3 cos 15. So from here we'll get fj1 sin theta is, what was fm1 was 378.6. 6 cos 87 plus fm3 was 87.7 cos 15 divided. Okay, it will not be divided by. Okay, this is fj1 sin theta. If we evaluate this, it will be 104.5. So this is coming from this equation, summation fx is 0. Now if we do this summation fy 0, what we will get? This y direction component is fj1 cos theta, fj1 cos theta, then it will be plus, because this will also be in the vertically upward direction and vertically upward direction. So the positive y direction, it will be plus fm1 sin 87 plus fm3 sin 15 is 0. And from here fj1 cos theta is minus sin 87 minus 87.7. If we evaluate this, it is coming minus 400.78. Okay, so we have got two equations. One is this one and one is this. fj1 sin theta and fj1 cos theta equal to this. So now if we now we can find out the fj1 and theta. So what we'll do, we'll divide 1 divided by 2. If we do this, then we'll get tan theta will be equal to 4.5. It is minus 0.26. From here, theta is coming minus 14.6 degree. So means our assumption was not correct. We have assumed that fj1 will act in this theta. So, and theta is coming negative. So it will be something like this. Theta will be in this direction. And fj1 will act along this direction. So theta is coming 14.6. Now, if we substitute, if we can use any equation here from equation 1. Equation 1, fj1 will be 104.5 divided by sine minus 14.6. It is coming minus 414.2 Newton. So fj1 direction will also be in the opposite direction. So we assume that fj1 was in this direction, but in actual scenario, fj1 will act in this direction, in the opposite direction, and at an angle theta. So fj1 will act in along this direction, and this is angle theta. So is this clear? This is the joint reaction force in the humeroradial joint. So we have found out the joint reaction force in one joint. Is it clear? Do you have any doubt? Okay. Now we can apply the same approach for find out the humero-ulnar joint reaction force. So for see for finding the humero-ulnar joint, we don't need to do this step, the first step. Why we did this first step? To find out this WR, but we have already got the WR, so we can subtract this WR from the actual load which was holding by hand. So we can directly apply these force equilibrium equations, then we'll get the humero-ulnar joint reaction force. But before that, we need to first draw the free body diagram of the humero-ulnar joint. So it will be something. This will be actual load was given 58. So, and we have got WR is 35.1. So it will be 58 minus 35.1 Newton. And this is W by 2. This is B. This is C. And in the ulna, there is only one muscle, M2. And this moment term we have estimated. In this case, we can, in the previous calculation, we assumed the first means our assumption was that joint reaction force will act in this direction and at an angle theta. So let us take the opposite assumption here, means we'll assume here that the joint reaction force will act in this direction, fj2, and this is theta 2. So let us see what we find that after doing the calculation. So if it comes positive, that means that our assumption will be correct. And if it comes negative, then it will means that these directions will be opposite. So we'll calculate using these directions. So first we'll do this. Okay, for FM2, this angle was, this is the brachialis muscle. This angle was 58. So we'll use summation fx0. If we do this, then okay, in my previous calculation, I did one mistake here. I think you also didn't see it. So it was, see, while considering these forces in the y direction, I should also consider these forces also, but I did not consider it. These two forces, W/2 and WR. But I forgot to consider it. So it should be F1 cos theta plus Fm sin theta. It should be minus W/2 and minus WR. Okay. So if we do the calculations again, L means with this minus 400.78, this will be plus W/2 is 83352 41.5 and so this is plus 76.6 and it will come minus 324.18. Now theta will be something different, so it will be 104.5. This is minus 0.32 and this is 17.8. Not so much difference, only difference by 3 degree. And now if we substitute it here, it is minus 340. Okay. So the directions were same, but only difference in the magnitude. So now in this case, if we do summation fx is 0, then it is fz2 dot cos theta 2 and minus fm2 cos 58. So from here, fz2 cos theta 2 is, we have found fm2 as 360.3 dot cos 58 will be 190.9. And when we do summation fy 0, then here fy, the y component of fz2 will act in the vertically downward, so it will be minus fz2 sine theta 2, and this will act in the vertically upward, plus fm2 sine 58 and minus w by 2 minus 22.9 equal to 0. From here, fz2 sine theta 2 will be waste 16.2. It is 254.9. So it is equation 1 and equation 2. So now if we do equation 2 divided by equation 1, then tan theta 2 is 1.33, and from here theta 2 is 53.2 degree. So in this case, it is coming positive. That means fz2 will act along this direction only, means the direction we have assumed previously. So now if we substitute theta 2, then in equation 2, its magnitude will be 318.42 Newton. Okay, so you can see this humeroradial joint reaction force is more than the humero-ulnar joint reaction force. They act along the same direction, but their directions are different. Means, sorry, they act along the different directions. So, and theta 1, theta 2 are different, and their magnitudes are also different. So, is it clear? If you have any doubt, you can ask. Okay. So, thank you. That was all for today. So, if you have any doubt, you can ask, or we'll meet in the next class, which will be on the next Friday. Yeah, thank you for joining. So we'll close the class now.